What happens inside a black hole? Can we travel back in time? Why is the universe even here? This is the type of chill questions that we're all asking ourselves from time to time. When we're sitting on the beach. This is also the kind of questions that Daniel Whiteson loves to talk about in his podcast, Daniel and Jorge Explain the Universe, co-hosted with Jorge Cham, the author of PhD Comics. And honestly, it's one of my favorite shows ever, so I warmly recommend it. And actually, if you've ever hung out with me in person, there is a high chance I started nerding out about it. Daniel is, of course, a professor of physics at the University of California, Irvine, and also a researcher at CERN, using the Large Hadron Collider to search for exotic new particles. And yes, these are particles that put little umbrellas in their drinks and taste like coconut. On his free time, Daniel loves reading, sailing, and baking. I can confirm, by the way, that he makes a killer Nutella roll. Oh, and I almost forgot. Daniel and Jorge wrote 2 books, We Have No Idea, and Frequently Asked Questions About the Universe, which, again, I strongly recommend. They are among my all-time favorites. This is Learning Bayesian Statistics, episode 72, where Alex gets to interview one of his favorites, science authors, recorded September 6, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayesstats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayesstats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
Hey folks, just a quick editing note. As you can probably hear, I'm having some troubles with my mic, which puts me in the very ironic position of being podcast host without a mic. So, thank you in advance for your patience and understanding. I am already looking into a replacement, so hopefully for the next episode, you'll hear me with a brand new mic with a great sound. And also a quick thank you to Tyler Birch, who is a podcast patron and was kind enough to put me in contact with Daniel Whiteson. So officially, thank you so much, Tyler. You made my day. Okay, now let's talk about physics and the universe. Just one last announcement. This Thursday, December 8, 2022, I'm co-hosting a meetup with PymC Labs, where an Estonian NGO that we worked with will tell us how they used PymC and hierarchical post-stratification to deal with noisy data. So if you're working in environments where uncertainty is high and data are sparse, especially in some strata of the population, well, I'd like to invite you. Of course, you're my favorite Bayesians. Just go to meetup.com/pymc-labs-online-meetup and register. This is a mouthful, so the link is in the show notes. Daniel Whiteson, welcome to Learning Bayesian Statistics.
Thanks very much for having me. Excited to be here at 8 o'clock in the morning.
Yes, I know. So now all the listeners know how cruel I am with all my guests. So thank you very much.
Be warned, potential guests.
Yeah, exactly. No, I have to say, you only do that with Daniel because I really love what he's doing. So I needed him to wake up for 8 a.m. so that we could record for about 5 to 6 hours. But usually we record in the evening. That's great. And I have actually your voice with me every day because I'm like listening to Daniel and Jorge Explain the Universe all the time. So that's very fun to have you now live with me. Today I was listening to the episode, The Cruise Tour of the Exoplanets. That was very fun. I love that one.
It's so much fun to talk about those crazy topics in science and to explore them and to take our listeners' minds to other worlds and distant parts of the universe. To me, it's just incredible that sitting here on this tiny little rock, we can actually know something about things that are happening so far away. It's kind of impressive.
Yeah. It's so weird, because it makes you feel both powerless and powerful at the same time. It's super weird. It's like, damn, this is like so empty outside, but at the same time, there is so many things. It's just like, it feels weird. But yeah, that's a feeling I love. Like, that's really, and I think you say that a lot in the podcast, like that feeling of like being surprised and understanding afterwards the very weird things that the universe has for us in store. This is an awesome feeling.
It is absolutely sort of digesting some crazy new idea about the universe and then thinking about all the people who never even lived to hear it. They lived their entire lives thinking the universe was one way and not realizing it was something different. And then thinking forwards to humans in the future who will make new, crazy, mind-bending discoveries and think about us as living in that ignorant age before they understood how things really were. So I like to think of ourselves as sort of in a long line of ignoramuses.
Yeah, exactly. And I think about that also sometimes when I'm like trying to remember that I know some stuff, but there is more stuff that I don't know. It's like, I remember that in the end, it's not being a long time since we know that we have to wash our hands, for instance, to be way safer from an epidemiological standpoint. And I'm always wondering, so like, because we make fun of those people, it's like, you just had to wash your hands and way less people would have died. And we did that for centuries. So I'm always wondering what will be you just had to wash your hands from the future. Like, what will the future generations look at for us and be like, these guys were so ignorant.
Something about podcasts. You guys just had to have more podcasts. You could save the world with podcasts. We're getting there.
Yeah, we're trying. Yeah. So actually, this is a very serious podcast. So I have to start very seriously and ask you, Daniel, what's your zodiac sign and what does it say about the universe?
Well, I was born in June, so my zodiac sign is Gemini, and it says absolutely nothing about the universe, except that humans have been struggling forever to try to make sense of it and have come up with like pretty crazy ideas for how to digest the universe and explain the things that seem to make no sense. If you are a human 20,000 years ago or 10,000 years ago, trying to understand why your child has died of disease or why a storm ruined your crops, you're going to wonder, what's out there causing all these things? Is it some other intelligent being, the gods? Is it some process out of your control? And so it's, it's just part of the rich tapestry of humans desperately trying to understand the universe around us.
Yeah. And you heard it here first, people. So astrology is a real science. That's the first thing.
It's storytelling. And there is an important part of science, which is storytelling, right? Science is, in the end, telling a kind of story. That doesn't mean that every story is science, but all good science does have a story element to it.
Yeah, and a human factor. That's also what I love in the work you're doing with Jorge, and what I try to do with the podcast also is like to make science more human, because I'm a statistician myself and it's very interesting. And I read a lot about physics. I'm a real nerd about that right now. And it's funny because each time you say that, people are really intimidated and they're like, oh, yeah, that's very powerful, but like so dry and, rational. But for them, rational is not a good word. And I'm always like, saying the contrary. I'm like, yeah, well, it's because you only see the result, right? But any big discovery in science starts with humans and even continues with humans. Like science was not something that came out of the universe. It's something like the scientific method is something we invented to answer the questions we were really curious about. So in the end, it is actually extremely human incarnated. And also I find it quite poetic, like when you look at the night sky and you see like big red dots, you're like, damn, that's a dying star. Is it dead? Like, yeah. Like dying star, but it's actually already dead. You're seeing something that already happened, but you're only seeing it right now. And this is always mind-blowing to me. And it's kind of poetic in a way.
I totally agree with you. And I think it's often overlooked that science is not this institution of knowledge. It's a human activity. It's by people, it's of people, it's for people, right? The questions we ask are the questions we want answers to. And, every time you read some paper about like the mating habits of hummingbirds, because somebody out there has decided that's the most important thing in the world and we have to understand it. And I'm going to spend 6 years crouching in a bush watching hummingbirds do it so that we can understand the answer. And so, science only gets pushed forward when somebody is like desperately curious about that particular question. And I think that's a really interesting and important thing to keep in mind as we fold in machine learning and AI into our science, that it can help power our science, but it can't replace us entirely, because you always need humans to be asking the questions and to be appreciating the answers.
Yeah, that spirit of curiosity, basically. And also that point that you often make, that the universe is like actually crazier than whatever you can imagine, because our standpoint is limited by anything we've ever encountered as a species. But like the universe probably has billions of planets and we only have 8. So very probably there are extremely weird things out there that we can't even imagine. I find that awesome. And like in the podcast episode I was talking about that I was listening today from you and Jorge about exoplanets, like there is actually at least one planet with 2 suns. This is incredible.
Oh, yeah.
Yeah, this is amazing. I'd like to just see what's out there, like how is it to live there? And I find that also fascinating that we can know that, even though it's very far from us.
Yeah, and actually it's much more common to have 2 suns than you might expect, because stars tend to form in clusters. You don't have like an individual star form in the middle of space. You have these big gas clouds that tend to collapse and form lots of stars. So you get binary star systems. You also get trinary star systems, which are mostly unstable because the 3-body problem is pretty tricky. But if you can get 2 of the stars near each other to form like a little system, a binary system, and then together with another star, they form like a nested binary system, then you can get like an almost stable configuration of 3 stars. And then you can just keep adding to that, with this nesting recursive star adding procedure. So yeah, the universe is pretty weird. In the end, it's an important statistical question, right? Like our solar system is 1 sample of trillions, right? How typical is it? How unusual is it? How weird are we and how normal are we? That's like one of the deepest questions in human existence. And in the end, it's a statistical one, right?
True. Oh my God, you should probably have a podcast or something like that, because you're very good at making segues. Yeah, exactly. And like this is something I discovered also when reading more about physics. Is like actually statistics is extremely important in the reasoning, in the methods, and in the reasonings, and in the conclusions. So that was reassuring to me, because there is a lot of things I don't understand in physics, but that I was like, okay, that's good. I like that. And I got this whole idea of like also of the multiverse. If everything is possible, then everything can happen and will happen. That's awesome. There is a planet with only horses, or only horses with my face on them. It's amazing.
And one with a podcast where 2 horses with your face on them are talking to each other.
True. Yeah, exactly. And they are visited by Iron Man, so does that, definitely that means there is a planet with superheroes, right? So then there would be the Avengers. That's cool. I feel like I'm taking Jorge's role now, talking about Marvel. Actually, I'd like speaking about humans and stories and superheroes, I'd like to talk about your origin story. I'm curious about how you came to the physics and stats worlds and how sinuous of a path it was.
Oh, that's a good question. And, I could tell you a podcast appropriate story about being transfixed by the night sky, ... But the answer is not really that simple. I did love looking up at the night sky as a kid and wondering about the universe and all that stuff. And so I tried astronomy. And then I discovered I don't really like standing outside in the dark, in the cold, staring into a telescope for more than a couple of minutes. And then I find it kind of boring. Like, you can't really do much other than look at stars and see that they still kind of look like points. Or you could look at the moon and like, well, how much can you really look at the moon? So I was inspired by astronomy, but I didn't end up becoming an astronomer because I didn't actually like the day-to-day work of it. And as I went through school, I really wasn't sure what I wanted to do, but I grew up in a town where physics was everywhere. I grew up in Los Alamos, New Mexico, and sort of like, physics is in the air. And it was just sort of like the culture to think that physics was the thing and it was the hardest thing. And so I thought, well, I don't know what I want to do, so I'll just try the hardest thing, which is physics, and I'll keep going until someone tells me to stop. And basically, here I am today. So I went to college and I studied physics and I was pretty good at it. And it was finally in my junior year in college when I took a class in particle physics and I understood, wow, this is the stuff, man. This is really interesting. I was, years into it before I actually got inspired, and it really touched my interest of the deep questions of physics. I loved taking things apart and trying to understand what the fundamental bits were. And then I got involved in research, and from there just kept going in particle physics. And I also was studying machine learning and computer science in college. I couldn't decide between physics and computer science, so I did both. And so I've been doing machine learning and computer science. Actually, everybody else in my family has a degree in computer science. I'm the only one with a physics degree, so I'm the oddball. My brother is now a professor at Oxford in machine learning.
I see. Damn, you pick the two right fields. Definitely. These fields are not outdated. You could have been unlucky and just pick two fields that just disappeared because of technology, but you did not. Were you advised by a superior civilization coming from space, or?
No, I just tried a bunch of stuff. When I was very young, I thought I wanted to do plasma physics because I thought fusion is the future. And boy, if we could crack that problem, we could solve everything. And I still think that's true. But I tried spending a summer doing fusion research and I just found it boring. There's something I didn't understand, which is really basic, which is that to do research in science, you need to not just be interested in the big questions, and that's not that hard, but you also have to enjoy the day-to-day work of it, because on a daily basis, we're not making big discoveries and solving huge problems. We're doing some craft. And in the case of plasma physics, it was like dealing with vacuum chambers and wrenches and pumps. And I didn't really like that. I thought it was boring and annoying. And I spent another summer trying condensed matter physics, which seemed awesome because we were zapping things with lasers to make new kinds of materials, which, wow, that seems amazing. Except that mostly it meant debugging the laser. And a laser has 5,000 components. And if each one works 99% of the time, the laser never works. So I spent a whole summer in a basement trying to make a laser work and got it to work for 19 seconds. And so I was interested in the questions, but not the craft. And then particle physics, of course, I was intrigued by the fundamental nature of matter. But it turned out that the day-to-day work was mostly writing computer programs to analyze data. And that was my jam. And so I love spending my days building little mental machines, little software algorithms to solve a problem. So finally, I found something where I was both interested in the day-to-day work and in the deep questions. And so that's why it was a good fit for me.
Yeah, definitely. Okay, so I want to dive actually a bit deeper into what you actually do, because it's something I don't really know about, because in your podcast or books, you talk about the general topics, but not really about your personal work. So I'm very curious about that. But from a meta standpoint, I really love that point of, when you can and when you're at that time in your life, really try stuff out and just it's okay to try stuff and find that boring and fail at it and then come back to it or go to something else. I think it's extremely important and something that not enough people do, at least in France. So just do it.
Yeah, I think it's one of the hardest things in life is to figure out who are you and what do you like to do? If everybody knew that, at 15, their life path would be so much more satisfying, right? But sometimes it takes until you're 25 or 35 to figure out like, who actually are you and what is it you like to do with your time?
Yeah. In a way, it sounds a bit discouraging, right? Because we have to understand the universe, but we also have to understand ourselves. It's like, when is that going to stop? I'd like to understand at least one thing. I know what my cat wants most of the time. That's something like, at least that works. So actually, can you define the work that you're doing nowadays and the topics that you're particularly interested in?
Yeah, sure. So I'm a particle physicist. That means that I smash particles together, and the hope is out of the debris from those collisions, we learn something new about the universe. Maybe we create a particle that hasn't been seen before. Maybe we identify a new force that nobody has identified before. But this is not something I can do myself in my basement laboratory here in California. We work with a $10 billion facility in Geneva, so the Large Hadron Collider, where they have a huge ring where we smash protons together at almost the speed of light. And so I don't have to build my own accelerator or build my own detector. I just have access to this data because I've helped be a part of the team that constructed the whole facility. And so to me, I get to ask whatever science questions I want. And to me, the interesting science questions are what's in the data that we haven't expected, that we haven't anticipated. We do these collisions, we smash protons together because we think there's something new to discover. We think there might be some new particles we don't know about or some new forces. And we have some ideas for what those are. Theorists have been thinking and drawing at the chalkboard and imagining what new particles might complete the story of the standard model. And they have specific ideas. And so some folks go and look for those. And they say, well, how do we see this thing? How can we identify these things in our collisions? And that's good and that's worthwhile. But to me, that's not as interesting as using the data to look for something unexpected. I think the most interesting discovery, the most exciting scientific moment would be if you found something and everybody said, what? That's impossible. It can't. What you've discovered is in contradiction with everything we've always understood. That's like my personal scientific fantasy. And so I'm trying to set myself up for that by looking for weird stuff, looking for stuff that's unexpected. And so that's how a lot of the statistics comes into play, is like, how do you analyze collisions looking for things if you don't have the alternative hypothesis, if you don't know exactly what it is that you're looking for?
Yeah. And in a sense, I really like that because the motivation is the same as people who are convinced that UFOs are real, coming from outer space, or some conspiracy stuff. The motivation in a sense is the same. It's this willingness to believe that something extraordinary is possible and can happen and is actually happening all the time in the universe. But what differs is the method to go there, because then with the scientific methods that you apply and the statistics that you use in your experiments, you can actually be somewhat certain, depends on the topics, but you can actually estimate also your uncertainty around your theories and be like, well, I'd really like this theory of, aliens visiting us and actually already having visiting us to be true, but I can't really believe it because of these other alternative theories that are much more probable. And I love that the motivation is the same and is actually something that seems to be in our species since the beginning of times, right? There was someone at some point who was like, what's behind this hill where nobody has ever been? So I really love that. But then the method comes into play, and then that's how you make discoveries.
Yeah, the truth is out there, and it's definitely part of being curious is allowing yourself to believe that something crazy could exist. And it's also interesting because it's very subjective. What you choose to look for, it comes from your curiosity. It comes from a very human place, the kind of thing you'd like to discover or the kind of question you want to ask. It makes me wonder, when we talk about the universality of physics, some people think that the physics we're uncovering about the universe is deeply true, that the particles are there whether we're looking at them or not, and that top quarks have existed since the beginning of the universe. And if aliens arrived, we could talk to them about these particles. We probably couldn't talk to them about what they like to eat for lunch or how they celebrate their birthdays or these kind of cultural arbitrary things, but that in physics, there's like something universal and deep and true. But I'm not sure I'm convinced by that. I think that a lot of the questions we ask have human motivations and the answers we tell have human stories. And so I think there's a lot of humanity there. I think it'll be really eye-opening if we ever do get to talk to alien physicists. And there's this subjective nature in all of our science. The theoretical community in particle physics is excited about one idea. It's called supersymmetry. That maybe there are these particles that we know, the electron, the muon, the tau, all these tiny little things that make up the world around us. But maybe there are also other particles. There's a copy of each one. The electron has a partner, the muon has a partner, the tau has a partner. Maybe they're out there and waiting for us to discover them. And they're excited about this idea for specific reasons. They look at the mathematics of their theory and they say, this would be prettier if there were these other particles. This would have a symmetry to it. It would be elegant. And, there's a subjective nature to that idea. And so that tells me that there might be a bias. There's almost certainly a bias. And I would love to explore the universe in a way that's more open-minded to things we didn't expect. There's lots of fields of science that are very, very exploratory. Think about like landing a rover on Mars. We don't know what we're going to find. You turn over that rock, there could be like critters under there. There could be anything. That's why we do it, right? We do it for the surprise factor. We don't want to go to Mars and discover exactly what we expected. We want to go to Mars and find something that blows our minds, right? And so that's what I want to do in particle physics, is to look for something weird and unusual. And, we have various statistical tools to do that, a lot of which have become much more sophisticated recently because of powerful machine learning that helps us define like what it means to be unexpected, what is different, what is an outlier, but also just sort of old-fashioned creativity. One thing that we do in particle physics is we look for a heavy particle decaying to two other particles. So, for example, when we saw the Higgs boson, we didn't actually see the Higgs boson. We saw it turn into two other things because the Higgs boson lasts for 10 to the minus 23 seconds. You can't actually observe it. You can only infer statistically that it existed because of the patterns of the things it leaves behind. Sort of like missing a car accident and reconstructing what happened just from the pattern of debris in the intersection. And so that's the kind of thing we do all the time, is look for heavy things decaying to pairs of light things. And so I had this idea, well, why don't we look for weird heavy things decaying to weird pairs people hadn't expected. Like, let's not look for heavy particles decaying to an electron and a positron. Let's look for heavy particles decaying to an electron and a muon, or an electron and a Higgs boson, or an electron and a W, these strange pairings that nobody had expected. And I proposed this to a theorist friend of mine once at a conference over coffee, and he said, well, that's ridiculous. I have 3 reasons why those things could never happen. You will never see those things in your collider. And I thought, awesome, because if you're convinced they can't exist and then I discover them, boom, Nobel Prize, right? And then a week later, I saw the same theorist at another conference, and he was like, actually, I have now 2 different theories that could explain why you might see those events. And so it made me realize that the reason nobody had predicted this or thought about it was just because nobody had been interested. The theoretical community has these trends, these ideas that they follow. And that's not a criticism, right? Every community is like that. But it does mean that it's possible to try to push the boundaries of that and think outside of it and think about what else we might see that could surprise us.
Yeah, definitely. And again, here, human factor extremely important, because in the end, it's people doing the research and having interests and trends and like also needing money. And some topics are more bankable. So yeah, for sure, this is definitely important. And I have several directions I could take now, but let's keep talking a bit about statistics, and then I have some quantum physics questions for you, because these my own personal misunderstandings. So it's my personal crusade. So yeah, actually, so this is a podcast about Bayesian statistics. So I'm curious, personally, are you familiar with those statistics, and are they useful to you personally in your work or not?
Absolutely. I mean, statistics is at the heart of everything we do in particle physics, because we don't have direct observations. It's not like looking for unicorns, where it might be hard to find it, but once you spot one, like everybody pretty much agrees you found a unicorn. In our case, we never see the particles directly. It's always statistical inference. We say we have this data and it's more likely to have been generated by a universe where the Higgs boson exists than a universe where it doesn't exist. And all we can do in the end is make a statistical statement and say there's a less than 1 in 20,000 chance of a fluctuation from a no Higgs boson universe to look like a Higgs boson universe. So absolutely, statistics is at the core of everything we do. And, I love that. I think statistics is super fun. I love the math of it. I love the logic of it. And I love the philosophy of it, So we definitely use statistics. And I love the sort of fundamental disagreements about what the questions are between Bayesians and frequentists. I find myself, and I don't know if this is going to offend you, more often agreeing philosophically with the frequentists about the nature of the questions that we're asking and how to answer them. But Bayesian methods are very powerful, and I often find myself using them in our papers and in our analysis.
Oh, yeah, that's super interesting. And yeah, it's not the first time I hear that point, that someone agreeing more philosophically with the idea of what is probability, and these kind of deep kind of axioms, in a sense, that are at the foundation of the two kinds of statistics. And in a sense, I would say these axioms are kind of like almost a subjective choice, where it's like, well, I prefer my statistics founded that way, but I prefer founded it that way. But then the methods and how you use statistics actually in your work, it's actually not the first time also that the same person telling me, I prefer philosophically the frequentist idea, but then the methods, when I use them, I prefer much more the Bayesian way, because it's just like much more intuitive to me. And also it's more useful to me because I don't have a lot of data and I have a lot of domain knowledge and prior scientific knowledge that I need to tell the models and so on.
Yeah, and it's not just personal taste. It's not just like, oh, I like cherry vanilla and you like chocolate. These are questions about what are the questions we are asking, right? You're talking about the fundamental nature of probability. In the end, statistics always comes down to really carefully specifying what it is that you want to know, because two very similar sounding questions can give very, very different answers. And, English is fuzzy. English is not a great language for communicating specific, quantifiable things, which is in the end why we are writing down mathematical theorems to describe the universe rather than paragraphs. But they do come from humans, right? And so it's what question do you want to know the answer to? Is it interesting to you to say, well, in 1,000 parallel universes, would there be a podcast with horse faces on them? That's sort of frequentist, right? Or is it more interesting to you to say like, well, we just don't know, and this probability describes our lack of knowledge about that kind of stuff? And so I think it's important. It's important that these questions are connected in the end down to the things we're asking, the things we want to know the answer to. It's just amazing to me that you get such different procedures based on asking very similar questions.
Yeah, exactly. And then depending on your question and context, one or the other kind of statistic will be more useful, for sure. It's like having different tools at your disposal and then just using the one that's most appropriate. But it's super interesting to hear that it's actually extremely useful in your work. And a question I often ask my guests is, do you remember how you first got introduced to Bayesian methods?
Yeah, I think that I took a class in statistics in college, and I needed it for particle physics, and I didn't understand why. And so I'll just take it. And I fell in love with it, and I'm learning about Bayesian Bayes theorem and feeling like it was really actually very closely connected to quantum mechanics and linear algebra in a way I hadn't expected. Thinking about Bayes' theorem, you can sort of think about projecting a vector into a basis space, which is something we do all the time in linear algebra and is an essential component of quantum mechanics. You have a vector in Hilbert space, and you're thinking about, the eigenvectors of that space. Well, it seems to me like, and I'm not a statistician or an expert in this area, but it seems to me like expressing a probability in terms of its conditionals using Bayes' theorem and using those expansions feels to me sort of similar to expressing something in terms of the basis states or the eigenvectors of the space.
I like that, yeah, indeed. So actually, do you have an example in mind from your work, ideally, that helps listeners, well, understand your work, but also how Bayesian sets can be helpful there?
Yeah, sure. We recently wrote a paper looking for very strange things in the collider. One thing that happens a lot in the collider is that you smash two protons together, and what comes out are two quarks, like an up quark and an antiparticle up quark, and they fly in opposite directions. But quarks, when they are created, you can never see them by themselves. There's so much power in the strong force that they feel that they're pulling particles out of the vacuum. So a particle like a quark immediately has thousands of other quarks flying with it. They're never by themselves. They create these sprays of particles that we call jets. And one idea that people have is, well, maybe sometimes these jets have dark matter in them. Maybe they don't just pull like normal quarks out of the vacuum, they also pull dark matter particles out of the vacuum. And maybe we're creating dark matter inside these jets. So we developed some techniques to try to tell these apart. Like, well, you have a jet. Is it from a normal quark or is it from a dark matter particle? Or is there dark matter inside your jet? So we used machine learning to develop a classifier that could try to tell the difference between these two. And that gives you some information. But in order to understand, in order to make a decision, like, is this jet from a quark or is it from a dark matter quark, you also have to have some idea about the prior probability of this happening. And so we use Bayesian statistics in that example to try to fold in the new information we get from the machine learning algorithm that tells us if it looks like a dark matter jet or a normal jet, fold that together with our priors about which one is more likely to try to get some sort of updated information, updated analysis about, whether a particular jet is likely to be from dark matter or likely to be from normal matter.
Okay. That's super cool. Do you have a link to that paper or a paper already that we can put in the show notes?
Yeah, absolutely. I have a link to a paper and a little tweet thread about it. It was actually a really fun paper because we did more than just try to throw machine learning at it and say, here's a black box that just tells us whether it thinks it's dark matter or not. We also try to interpret the network. We try to translate the network into a basis space of sort of human concepts about these jets. We asked theorists to define, can you define a space of ideas? Can you say, what are all the possible ways you could think about jets, all the possible sort of operators you could imagine on jets, ways to analyze it, like primitives? What are the primitives of the language to think about jets? And then we took this neural network and we try to map it into that space. We say, can we express this neural network, which is just in the end, a complex function with lots of weights, into the space of sort of human ideas, translated back to the human mind, and then look at that and understand what is it doing. And so that was a really fun project because we got a little bit of insight into not just whether we could tell them apart, but how the machine learning was distinguishing one kind of jet from another kind of jet.
Okay. And actually, I'm curious how much of your job is trying to kind of translate knowledge that a non-human could understand. So a computer or some other species that can see and feel more things than us with our limited senses, to then the language and senses of humans. I'm thinking about that black hole image, for instance, where we're not really seeing the black hole, but we're seeing something that we can see and that is accurately depicting that black hole. But I'm guessing that it's an important part of the work, right? Because then you need to convince not only the scientific community, but then also the general public about those things. So I'm curious, how does that work for you, and how much of that work that means for you?
Yeah, I think that's the central project of physics, right? Is explain the universe, the unfamiliar, in terms of the familiar. You picked a great example, the black hole. What is it that you would actually see with your eyeballs if you were there? That's not what you would see, right? That image is reconstructed from photons of all different wavelengths. Maybe even crisper example is the James Webb Space Telescope. Everybody's been drooling over these pictures on their computer screens, but realize that the James Webb Space Telescope, it sees photons in the infrared. If your eye was there instead of the telescope, you would see something, but you wouldn't see those pictures because those pictures come in an invisible wavelength. If you like literally were looking at an image of the photons from the James Webb Space Telescope, it would just be black. You couldn't see it at all. They've shifted it up in frequency so that you can understand it. And that's a literal example, but it's also a metaphor for everything we do in physics. Everything in physics is like that. You know, what is a photon? Well, we try to describe a photon, which is a very strange thing we've never really experienced before or deeply understood in terms of things that we feel comfortable with. It's like a tiny little ball, so let's call it a particle. No, it's sort of more like the waves we see in water, so we call it a wave. It's really, and then sometimes we say, oh, it's kind of both, or it's a combination of the two. Really, it's neither of those. It's something else, something weird, something different we can't ever really grasp, but we try to. We try to explain this new thing sort of in the basis set of the ideas we're comfortable with. And so that's everything we're doing. And it just depends on like, what is the basis set that you need to translate to? Are you talking to another physicist and they have sort of the same toolkit in their mind so you can just talk about those things? Or are you talking to somebody on the airplane and they don't have any of those ideas and you need to translate it into basic ideas that they are familiar with that you can talk to them about? So to me, that's the central project of physics, is translate the universe into the human mind, but at various layers.
Yeah, definitely. It's funny because I started finally reading Stephen Hawking's book, A Brief History of Time. And the first chapter is exactly like about that, like the motivation of physics and what that means to work, to be a physicist. So I found that definitely interesting and echoing what you're saying right now.
Oh man, Stephen Hawking is always ripping me off, you know?
Yeah. That must be frustrating, isn't it?
Give all the credit, man.
Yeah, that's hard. I know. I've been there.
Just because he came up with these ideas before I did, like he should get credit for them? I mean, is that how these things actually
work?
True,
I know. Yeah, well, for me, it's Laplace. Like these guys, I have the same ideas as these guys, just because it's later, I don't get any credit. Like, life is unfair.
Life is unfair, exactly. In another universe, you are a famous statistician and he has a podcast.
Exactly. In that universe, it's called Endorian statistics. And we're talking about Daniel Whiteson's Brief History of Time, you know.
I'd check out that podcast, yeah.
Yeah, I would check out that
Laplace
book.
And Stephen Hawking complaining about the two of us. Yeah, let's hear that podcast.
Definitely. I really like that. And actually, to go back to the paper you were talking about, so again, we'll put it in the show notes for people who are interested, because I have a very cool, nerdy audience who loves papers and show notes. So definitely we'll put that here for you folks. And I'm wondering if there is one or two main difficulties that you encountered during that project, and most importantly, what you learned from those difficulties.
Yeah, that's a good question. It was definitely not an easy project. It's one of these projects that we thought was going to be pretty quick. We had all the tools, we had all the techniques, we had all the data. We're like, oh, that's going to be a quick one. And then a year and a half later, we're still struggling to get the paper out. It always comes down to understanding what your results are. And the results we got were sort of confusing at first. We discovered that these difference between the dark matter jets and the normal jets depended on particles that were very, very slow moving. It seemed to be mostly not in the fast stuff, not the particles that were zipping around with a lot of energy, but the very slow moving stuff, things we call soft, low momentum particles that really distinguished the dark matter jets and the normal matter jets. And so we struggled for a while to try to understand why that was and to think about what that meant and to come up with some ideas, because in the end, you can't just like do a paper and say, here are the results, done, we're moving on. You have to explain them. You have to say why they make sense. You have to try to fit them into the scientific conversation. Say, look, this is what we've learned. And so we were surprised by the results we saw, and it took us a while to come up with an understanding, a theory at least, a sketch of why it might be that the very, very slow-moving stuff helped us distinguish the dark matter and normal matter jets more. And it was also sort of discouraging because the slow-moving stuff is the stuff that we don't understand very well. Quantum field theory describes how particles fly around and how they're generated. And in principle, a particle flying through the universe is always generating other particles. An electron is never just by itself. It's surrounded by a cloud of virtual particles. Mostly we can ignore these because they're very low momentum. There's an infinite, as you go down to smaller and smaller momentum, the probability to generate a particle out of the vacuum goes up and up and up until eventually it goes to infinity at zero momentum. And so you have like this infinite sum over very slow moving particles. So mostly you can ignore, but because usually we're interested in the fast moving stuff. And so to have your signal sort of buried in the slow moving particles meant that it was going to be harder to understand, because that's sort of like the swamp of quantum field theory.
Okay, yeah. That does sound complicated. Actually, it's a perfect segue, because for this episode, I asked my nerd crew, so my colleagues and my other open source developers, friends, and if they had any stats physics questions for you. And one of them, Ben Vincent, asked me a bit more about, that cat for quantum physics, and in particular, is it that the cat is literally alive and dead, or that you have a 50-50 belief that the cat is alive or dead and you just don't know? And then there were a whole debate among the guys, because some of them have some physics background, and so these guys were saying, yeah, actually that's just that's not really that was more of a means to demonstrate the absurdity of the Copenhagen interpretation at the time, and that's not really the good experiment to understand that. There are better experiments to understand that concept. So, can you help us here? Tell us what this is supposed to explain in the end, and how good experiment would look like to understand that phenomenon.
All right. The fundamental randomness of quantum mechanics. Let's get into it. There was this revolution in the early part of last century where people discovered that our explanation of the universe as mechanistic, that every experiment could be predicted by its initial conditions, that if you knew enough about the particles in your system, then Laplace's demon, right, or the Andorian demon could tell you what was going to happen. And quantum mechanics says that that's not the case, that there is a fundamental random nature to the universe, that you have the same initial conditions, you can get different outcomes. And that's kind of mind-boggling, right? Because you expect if you throw a ball, or you kick a soccer ball the same way twice, it will go the same direction. That's your intuition. But quantum mechanical particles don't follow the same rules, and there's this probability distribution for what's going to happen to them. And so that didn't sit very well with a lot of physicists for a long time. And they thought, maybe it's not the case. Maybe it's not really random. Maybe there's some hidden information. There's something that's secretly determining what's going to happen. We just don't know of it, right? And so it goes to the heart of this sort of Bayesian versus frequentist question. Is it actually determined, but it's not, but it's just that we don't know enough information. We don't have all the information. But in principle, some super intelligent alien could gather the information to predict these experiments? Or is it really actually random? In 1,000 hypothetical universes, you do the same experiment, you actually will get different outcomes, right? So there's the Bayesian versus frequentist approach for you. And so people were wondering about this. And as you say, the folks who thought it was ridiculous to imagine that there was a random element to the universe came up with these examples, these ways to try to illustrate the absurdity of having a random element. And one of the hardest parts to grapple with is this idea that the universe can maintain an uncertainty until you've examined it, right? So you imagine some particle has a probability to go left or to go right in some experiment that you've done. And the question is it actually going left and actually going right? And then when you look at it, you just learn that, or that the universe has kept that uncertainty, it maintains the possibility of going left and going right until somebody asks the question, and then it decides. Where is the universe invoking its random number generator, right? And it's very uncomfortable to say, hold on a second, are you saying that it depends on when we ask the question? The universe is not just operating on its own and we're, peeking into it, that we're actually changing the answer by asking the question, or that the question you ask the answer you get depends on the question you ask. And to me, that's really resonant with statistics, right? Because the answer you get really does depend in statistics on exactly the question you're asking. And so, there is this famous experiment, the double slit experiment, where it demonstrates that by asking a question about the particle, you are forcing the universe to make a decision, and you lose some of the quantum mechanical effects that can only happen if there is uncertainty. But I think probably the most interesting experiment, the one that really puts a nail in the coffin of this idea that the universe has all this information, that it really is deterministic, is Bell's experiment, which is again very statistical. It introduces yet one other concept quantum mechanically, which is entanglement. It says, well, create some particle like some electron, and that has a possibility to spin up or spin down, for example. And we're talking randomness here, so we say the electron has a 50% chance of being spin up and a 50% chance of being spin down. But now create it with a pair, create it with a partner, another particle that has to have the opposite spin. So electron number 1 can be spin up or down, and electron number 2 can be spin up or down, but they have to be opposite. So if electron 1 is spin up and electron 2 is spin down, then electron 2 has to be spin down, and vice versa. And the interesting thing about this is take those particles and now separate them over very, very long distances. So this is Einstein's thought experiment. He says, if quantum mechanics is really random, if it's maintaining the randomness of both electrons simultaneously, then something really weird is going to happen, which is you pull these guys apart, and you bring them like a light year apart, and you look at one of the particles, and if quantum mechanics is really random, then you're telling me that it's uncertain which spin this electron has until I look. But now the other one I know has to have the opposite spin. So if I look at electron 1, then electron 2 suddenly, across light years of space, instantaneously goes from being uncertain to having to have the opposite spin of electron 1. And so this weird sort of action at a distance was very strange for Einstein, and he thought it can't possibly work that way. It's one of the great examples of somebody saying, look, here's something that quantum mechanics predicts, which is bonkers, and therefore shows us that quantum mechanics is wrong. But then people go out and they do the experiment and they confirm the bonkers prediction. They're like, oh yeah, well, it turns out actually the universe is bonkers. And so all is good with the theory. The problem is just our digestion of it. And so there's a series of Bell's experiments, which try to tell the difference between the two scenarios. One is that both particles really are uncertain until you look at either one of them, that the universe is like is not determined yet which one is up and which one is down until somebody asks a question and collapses the possibilities. And the other possibility is that they somehow have some information, that they've always been spin up or spin down until you look. And Bell's experiment is a very, very clever way to try to disentangle these two possibilities by rotating one of the particles a random number of degrees and using correlations between the spins at those different angles to try to disentangle it. It's a very subtle experiment. And so to me, that's one of the most interesting experiments in the history of quantum mechanics, and one of the most surprising, because it shows us that the universe really is fundamentally different from the way that we thought it was.
So in the end, the answer is the first option, right? It's definitely undetermined until you look inside the box in a way.
Yeah, and so the answer is that it's not determined by some little piece of information the electron carries with it. It's not like there's some little pocket where the electron has some detail in it that's going to determine it, and it just waits until you ask the question to tell you. It's consistent with it being random and only collapsing at the last moment. There's a lot of loopholes to this experiment, a lot of wrinkles, and one other alternative is that it is deterministic, but that there's some like global universe spanning function called a pilot wave, which is organizing everything across space and time and global and instantaneous. So the most accurate way to describe Bell's experiment is to say that it rules out any local hidden information. It doesn't rule out a global hidden information, something which is organizing the whole universe. And Bell himself actually thought that that was the best way to interpret the experiment. He said that quantum mechanics is non-local, that there's something weird, when you're making a measurement here, it affects things over there instantaneously. That convinced him that there's this pilot wave spanning the whole universe. It's called Bohmian mechanics. It's a whole different view of the same experiments. But yeah, it's also consistent with quantum mechanics being purely random, being really probabilistic, which is hard to get your head around. That being the fundamental nature of the universe.
Yeah, definitely. And I can see that also in like the models I work on are probabilistic, and it's incredibly hard to explain people who are not at all in the statistics field that yes, things are probabilistic also sometimes. It's just not that you don't have enough information. It's like sometimes it's really probabilistic. And that's really interesting because our brain really wants things to be deterministic, right? Like even Einstein's brain wanted that to be true.
Yeah.
It's actually super interesting to hear that he was really not believing that. And actually, when was the Bell experiments? When were they done?
So they were proposed in the 60s by Bell, and the first versions of them were done in the 70s. But they're very hard to do, and so people have developed better and better versions with like closing more and more loopholes. They're still doing them. I think the latest one I read was from 2015, where they have the two particles really, really far apart, because you want to make sure they're super far apart so there's no time for like light or any sort of information to communicate between them. You want to look at them in a way that instantaneous communication would have to be faster than light in order to somehow coordinate between them. So it's a whole area of study. I'm really interested in what you said a minute ago about people not being familiar with randomness. I feel like a lot of people think they are familiar with it. Like they think, well, a die is random, or a coin is random, right? Or the weather is random. But those are actually not great examples, because those are situations where if you did know enough, if you knew exactly how somebody flipped the coin or rolled the die, you could predict it, right? It's apparently random. And in our lives, we have almost no experience with true randomness, right? All these things are pseudo-random. Even the random number generator on your computer, right, is not actually random.
Exactly. And it's like, what does that mean? It's purely random. It's just like, I think I always forget, but I think in the statistics world, we call that epistemological uncertainty, which basically means, well, it's just like there is the knowledge somewhere. It's just that we don't have that knowledge and we have to describe it with degrees of uncertainty. But the knowledge is out there. Here, what the experiments show is that no, actually the knowledge is not out there until you look for something, for that electron or that particle. And that's pretty amazing.
It's really strange to try to wrap your head around this idea. You do the same experiment twice. You like prepare it exactly the same way. Maybe you shoot an electron at a target and you can get different outcomes. It can come off at a different angle every time. And it makes you wonder, like, why this angle this time? What is determining that? What process is choosing that? Is the universe have in it some like source of random numbers it's pulling from? Like, that's crazy. But it's also really useful if it really is random, because we need random numbers in all sorts of applications, right? In making codes and in cryptography and stuff. And so I know folks who try to use like cosmic rays, which are quantum mechanical, to try to generate real random numbers.
Yeah. So actually, do we know more about that? Like, because I'm guessing it's a question like that's very important in physics. Like, how do we understand that randomness? Like, and because there is still the possibility, as you were saying, with, I don't remember the wave or something like the name of the wave. There is actually still, it's coming from a knowledge that's out there, but we still don't know. Or like, is it true randomness? So I'm guessing that it's an active field of research. So what basically do we know about that?
We don't really know very much. We have these different interpretations of these experiments. One of them is the Copenhagen interpretation that says things really are random until you look at them. But that's really problematic because nobody really knows what we mean by it, and then you look at them.
Yeah.
Because, for example, these quantum mechanical particles, they can interact with other quantum mechanical particles and not disturb their probabilities. They can maintain the uncertainty when interacting with other quantum mechanical particles. But they can't maintain that uncertainty when they interact with you or your eyeball. You can't see something quantum mechanically. You can't say like, oh, this photon hit my eye and it might be here and it might be there. You don't like see the different probabilities. You see one photon. What we don't understand about that is, well, your eye is made of quantum mechanical particles. Everything is. So where's the difference? Where's the threshold? Where does something become classical, where it forces the universe to collapse it, and where does it stay quantum mechanical? It's not well defined. And so that's a big problem. And another theory is this Bohmian mechanics. It says, well, it actually is all deterministic. It's just organized by this crazy global pilot wave. That's not a very popular theory, mostly for historical reasons, because there was a proof by John von Neumann that ruled it out, but it turned out that proof was wrong. And just because von Neumann was such a genius and so influential that it sort of buried that whole idea for decades before Bell actually is the one who dug it back out of the weeds and tried to make it popular again. And then there are other theories called like many worlds quantum mechanics that says all of those things happen. When there's a probability for something to happen, the universe splits and every possibility happens in a different universe.
Oh my God, that would be so amazing.
Yeah. And in that universe, it's really hard to even define what do you mean by probability, because everything happened, right? Everything happens. So everything has a unit probability. So those folks have a sort of a hard task to define, like, what do you mean by the probability for this to happen or that to happen when everything is going to happen? So the answer is that we're at that moment where people are going to look back at quantum mechanics in 100 years or 500 years and be like, what were they thinking? They just had to wash their hands. The answer is probably so obvious and right in front of us. We just are not thinking about it the right way. And somebody out there, maybe one of your clever listeners, is going to put it together and help us understand it.
Oh, yeah. Well, please do so. And then if it's because of us, then definitely mention that episode in your Nobel Prize acceptance. That'd be the least you can do. Yeah, damn, that's amazing. So it's like, and that would be incredible that the answer is obvious in a way, right? Because it's like, this would be a huge answer to big mystery that we still have about how the universe works. That would be amazing that the answer would be like, oh yeah, of course. Why didn't I think of that?
Yeah, well, you can often do that in the history of science. Sometimes people make discoveries based on data that's already out there. Like Einstein won his Nobel Prize for the photoelectric effect, explaining that photons really are little quanta of energy, based on experiments he didn't do. He just read about them. Somebody else could have read about them and made the same ideas and, won the Nobel Prize. And so sometimes it really is true that the information is there. You just need somebody to come along with the right idea.
Yeah. I mean, that's also a basis of the idea that knowledge is a community, that personal knowledge is kind of an illusion because we are all participating in that community and building it, and that actually the ideas of relativity, even from Einstein, you can already see them in some writings before, from Poincaré, for instance, where you have already some formulas talking about that. But then I just it's an idea of the time and it builds up, and then someone with an amazing intelligence comes and unifies all that. But it's kind of already there. I find that pretty incredible because also it's important. I find one of the most difficult things when you do science education is not to turn some scientists into heroes, because then, and that's also kind of the problem of the Nobel Prizes, right? Because then that turns those people into prophets, and well, that's not good. And it's something that you often say, right? That if Einstein came back to us and was like, oh, actually the Earth is flat, well, you should not believe him, even if it's Einstein.
That's right. And I often hear Nobel Prize winners talking about things they don't know anything about, because people think, oh, you won a Nobel Prize in physics? Let's ask you about climate change, or let's ask you about education policy. It's like, well, these people don't know anything about that. It doesn't make them geniuses in everything to win the Nobel Prize.
Yeah. And even in their old field. Yeah, so that's important for sure. I mean, but I want to be mindful of your time because we could still talk about that. I have so many more questions, but before closing up the show, though, I'm curious about these experiments, these Bell experiments. So did Einstein learn about those, or was he dead already? Did he have the result? Did he discover that actually he was wrong on that and the universe was actually much more random than he thought?
No, Einstein died, unfortunately, before Bell wrote these papers and saw these experiments. I would be really curious to know what Einstein thought of these experiments. Probably he would respond with oh, that's interesting. Here's another even crazier set of experiments for you guys to go do. But no, unfortunately, we won't know what Einstein thought about these experiments.
I see.
It's a cool alternative history. Somebody should write that science fiction novel.
Yeah, for sure. Yeah. And so last question about that one. How do you do that? How do you see those particles, right? Tell us quickly, what does that mean to have two particles like that who are bounded? And how do you identify them first? Can you make an error, thinking, oh, particle A here has to be bounded with particle B? Can you make an error in these bound? And actually you took another one, which was spinned up, but actually you needed another one because that one was not bounded with the first one. What does that mean? And so you can feel free to like give a general answer. And if you have resources for people to go and read about those experiments, also like, I know, some YouTube videos or things like that, feel free to also share with the listeners and we'll put that in the show notes.
Yeah, that's a great question. These correlations between the particles, like particle A and particle B having opposite spins, they come from a local process, like they are created that way. So you take, for example, a photon and you let it decay to an electron and a positron, and you know that the spin of the electron and the positron together have to equal the spin of the photon. So you create this entanglement, this condition, this constraint on the particles because of the initial conditions of your system. So you're just not like that you're going out there looking for particles and saying, I think this one might be connected to that one. You're creating this condition. You're instilling this correlation in them from how you've created them. And the trick then is to keep them isolated, is to create these particles and not let them interact with anything until you are ready to make your measurement. And the way that you can measure the spin of a particle is that a particle, if it has electric charge, its spin gives it a tiny little magnetic field. And you can pass it through a magnet and see, like, does it go left or does it go right? And that'll tell you whether it's spinning in one way or spinning the other way. And this whole idea of quantum spin is also very confusing. You know, this is a topic we talk about. It's a property of a particle that's related to actual spin, but it's not like literally that the particle is a little planet that's spinning the way you probably envision in your mind, because they've done the calculation. And if that were the case, the surface of it would have to be going faster than the speed of light. And so that's how you actually measure these particles. You pass them to a magnet and you see which direction they go.
Fascinating. That's awesome. The universe is amazing. Cool. Do you have any resources for people that you can point them to?
Actually, in our podcast, Daniel and Jorge Explain the Universe, we just tackled this and did a whole podcast episode trying to pull this apart and talking about the various interpretations of it in great details. But there are lots of great explainers out there. So if you just type Bell's experiment into YouTube, you can see there's a nice video from PBS Spacetime and lots of other folks.
Okay, perfect. So definitely I put that in the show notes. Cool. So before asking you the last two questions that I always ask people, quickly, have you heard of quantum Bayesianism?
Quantum Bayesianism? No.
Me neither.
That sounds super fun.
Me neither. And I was like, it's Ben also like from PMC Labs, the company we work at, and he was like, you need to ask Daniel about quantum Bayesianism. I don't know what that is. And yeah, me neither. So apparently you don't either. So that's good to know. Okay, so before letting you go, Daniel, I'm going to ask you the last two questions. I ask every guest at the end of the show. So the first one is, if you had unlimited time and resources, which problem would you try to solve?
Wow, unlimited resources. That's pretty amazing. Unlimited resources and time. I love that. This is actually something I do with my research group to try to teach students to be creative about their experiments, to say, like, what question would you like to answer? No limits on funding or no practical boundaries. And they come up with some pretty crazy stuff. I think that, one of the deepest questions in the universe is about whether what we're discovering, is it something we're revealing about the universe, or is it something that's just part of the human mind? And to me, I want to answer that question by talking with alien physicists and saying, like, do you guys see particles also? I mean, this Higgs boson thing, is that really a thing, or is that just part of the way we tell stories about the universe? So Infinite Time and Money launch a fleet of artificial intelligence powered self-replicating robots that expand and reproduce to explore the entire galaxy to find alien intelligence that's technological and ask them questions about their theories about the universe, so that we can compare them with ours, and also so we can, jumpstart, like, maybe we can find some species that's been doing physics for 1 billion years and we could just, like, fast forward our knowledge. Or maybe we discover that, the alien mind asks such different questions that we can't even grok the questions they're asking, not to mention the answers that they have found. I think we would learn a lot about sort of the nature of the universe and our relationship with it if we could visit all of those alien species and ask them questions about how they think about the universe. That would be my personal way to spend an infinite amount of money and time.
Nice. Yeah, I am not surprised that you're answering something related to aliens. It's perfect consistency on your part.
Thank you.
And so second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
That's a really hard question. There's so many good options. I think for me, one of the most interesting things is discoveries that seem obvious in hindsight. Like we look back in history and be like, oh, well, I could have done that, or I could have figured that out. That seems obvious. And it seems obvious to us because we're in the future of it, not just because somebody had the idea, not like, oh, I could have had the idea for Spider-Man. It's because the idea has so changed the way that everybody thinks that it's just like now inherent in the way we're thinking. So for example, I'd like to talk to Galileo because Galileo did something really amazing, which is he disproved Aristotle's physics, which had stood for thousands of years. He did it in an afternoon with a couple of sticks and a ball. And he did it just by actually going out there to test it. He just did the experiment. Aristotle had these ideas about physics and he thought he could derive the way the universe worked just by thinking about things. He didn't have any need to go out and actually try them out. And Galileo was like, well, let's go do the experiment and see if this works. Oh, turns out, Aristotle, you were wrong. So in an afternoon, topple an idea which is thousands of years old. What is that like to be in that moment of transition where you come up with a new way to explore the universe and to develop ideas? So, he sort of straddles that boundary. He's in the old world, grew up with the Aristotelian ideas about physics, but using new ideas now to explore the universe and make shocking discoveries. I'd love to hear about what that's like to sort of be on the boundary, what kind of crazy intellect it takes to come up with the bravery to try something so radical and yet so easy.
Yeah, me too. Make sure to invite me to that dinner.
I'll bring my microphone along. We'll record it.
Oh, perfect. And we'll eat some Nutella. Galileo needs to discover Nutella. For sure. Well, it's time to call it a show, unfortunately, because we don't have unlimited time for that podcast episode. But thanks a lot, Daniel. As expected, it was fascinating and passionating. I really hope that listeners learned as much as me. I really encourage them to check out your podcast, Daniel and Jorge Explain the Universe. I personally binge listened to it, so definitely go there, people. Also, your book with Jorge, We Have No Idea. I really loved it. And I still remember when someone introduced it to me, I was in Buenos Aires in a really, really good parisha, so steakhouse. And that guy told me, oh man, you have to read my favorite book of all time. And then he pulled up We Had No Idea.
Oh, that's so nice. Well, if any of your listeners have questions about anything we've talked about, they're very free to email me. I'm daniel@uci.edu. I answer all my emails. So if you have a question about what we talked about or physics in general or the universe, feel free to reach out.
Yeah, please do. As you heard, Daniel is amazing at explaining physics. So as usual, I put resources and a link to your website in the show notes for those who want to dig deeper. And thank you again, Daniel, for taking the time and being on this show.
Thank you very much for having me. It's been a lot of fun.
Well, you bet. Well, come back anytime. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.